Hello, ma'am. Am I audible?
Good morning to all of you. So we can start our session number 10. Our speaker, Mr. Rajkumar from BI Solution, he is already present with us. Sir, now the session is over to you. You please start the lab session.
Hello, everyone. Could you please just confirm whether my voice is indeed audible now?
Yes, sir, it is clearly audible.
Yeah, thank you very much. So, yeah, thank you very much for having me once again. So, with that being said, without further ado, let's continue to do today's session. Let me just share my screen. So, yes, I guess my screen is right now audible. I mean, am I visible? So, let me just go ahead to the yes. So today yesterday we have seen about the IIoT architecture implementation using NI technology. Okay, so we saw what are the key aspects of implementing IIoT, what are the things which we need to consider, and what are the parts which are available, which needs to be considered and included so as to have a full IIoT stack, implemented using NI LabVIEW software, right? So today we are going to try and implement one such implementation, and what are things which we need to consider. Those things we are going to see. Okay, and how other people have done it. Okay, so we're just going to have a gist of it, right? So yeah. So first we are going to see about the condition monitoring. Okay, because we are going to see about the remote grid asset condition monitoring system. Okay, so let's try and first understand the condition monitoring. Then what does NI provide for us, okay, in order to implement the system which can do condition monitoring in power system? Where are the areas where it can do condition monitoring? And what tool does it help? What tool does help us to implement this condition monitoring? Okay, so most probably the data from the grid will be raw data. Okay, so we need to have some toolkit, okay, which is going to convert this raw data into something which is analyzable and which could be subjected to some sort of analysis. And that data should not be local, okay, it should be pushed somewhere. Okay, so a cloud technology could be used. Okay, and this cloud technology, the data from the actual edge node, okay, it should not come to an actual computer, and from the computer it should not go to cloud. Your edge node itself should be capable of connecting directly to internet. Okay, and it should be these data should be viewed from anywhere over the world. So in order to view it anywhere from the world, okay, so you need to have a centralized cloud technology. So one such technology, there are several technologies which we have discussed yesterday. Okay, there are many companies which provide the cloud solutions. Okay, for example, IBM and Amazon. Okay, so these companies are typically involved in development of IoT based solutions for several stuff. Okay, out of which we are going to use Google's real-time database. Okay, so for number one, why the Google for real-time databases is easy to work with. Number one. Number two, it is free. Okay, for some usage. Okay, after which if you're going to transfer a lot of data, then probably you might need to think about pricing. Okay, but other tools, other cloud is also equally more efficient and involve more tools, but the pricing is involved even for trial. Okay, so for our reason, just to look at how you can implement things, okay, we'll go with Google. Then later on, if anything requirement is coming up, we can probably later on talk about implementing using other tools as well. Okay, but first let's examine what are things which we can make use of. Right. So yesterday we wanted to talk about condition monitoring. Okay, so we saw what are the tools which can be used for condition monitoring. Okay, but let's still look about it. So condition monitoring or mission condition monitoring, okay, is going to be a system, okay, which is going to monitor the condition of the operating condition of a system during runtime. Okay, so it's going to analyze, it's going to acquire and analyze data in real time during the operation of a machine. And basically this was done, by several, this should be done by several engineers who will monitor different types of parameters individually. They'll take notes, they'll maintain a graph. This was probably like few years ago. Okay, so nowadays everything has been computerized for past 20 years or so. Okay, but this what picture we are seeing, okay, this was like several years ago, like 30 to 35 years ago, where an individual engineer will be monitoring all these things. Okay, but in order to computerize all these things, okay, so as to avoid measurement error due to operator uh, you know stuff and so on and so forth. Okay, probably computer based measurements have come into picture. Okay, in order to make use of measurements by people, okay, we will automate it. Right, so while automating it, you can use computer based tools for acquiring data and analyzing the data, and also continuously monitoring it. Okay, let's say 24/7. So, but why do we need to do this condition modeling in the first place? So when you take a mission, okay, let's say for an in case of, let's say for motor for now example, okay, so its condition is going to be at first during the installation, okay, its condition is going to be perfect, okay, nearby to perfect. There's no flaw, but due to eventual wear and tear, okay, due to continuous usage, you might start to see that its condition is going to start to wear. Okay, the vibration is going to come, noise is going to appear in a few weeks. Okay, then in few months, slowly the heat starts to develop. Okay, this heat was not first a continuous stream, but due to noise and vibrations, okay, your molecules tend to vibrate and it started to develop heat due to friction. Okay, then smoke starts to come up. Okay, and suddenly emergency stops. So this is like generally which happens. Okay, but this happens when you don't monitor and when you don't take heed to your the condition of your machine. Okay, but we need to have system which is going to predict when these things are going to happen. Okay, so initially we don't see anything, but slowly, okay, you might, if you use a system which is going to monitor this, okay, so this system should be capable of estimating how much time is it going to, due to current operation, how much time is it going to get vibrations. Okay, probably in after 3 months of operating, you might start to get vibrations. Okay, prediction. And after this, okay, after starting to get the first vibration, in few weeks from now, okay, you might get noise. Then after that, you should be able to predict when you are going to exactly it's going to fail. The reason why we do this is, okay, possibly by if you know how when the vibrations is going to come, okay, you can predict when the noise is going to come. Okay, and before this system goes to produce heat, we should probably schedule maintenance. Okay, so when noise comes up, probably we need to fill the machine with appropriate levels of oil or some other maintenance. Okay, should be done. Okay, appropriate maintenance for different types of machines. Right, if it's a transformer, okay, transformer will also have different types of maintenance should be done. Maybe to change the transformer oil. Okay, to check the isolation and all these things. Okay, and to check the quality of to check the the strength of the coil, okay, internally. All these things should be checked. But instead of checking it over a set period of time, it's better if you have a condition monitoring. This is going to say, okay, your system needs some sort of maintenance. Okay, that maintenance could be, let's say, in 3 months. Okay, or sometimes due to we have seasonal change in operation of the grid. Sometimes during the summer, okay, the load will be high, and during the winter also the load will be high. Sometimes the load will not be that much high. Okay, so due to the fluctuation of load requirements, due to wear and tear, due to that, okay, so you sometimes we may need to do maintenance within 2 weeks or 3 weeks. Sometimes for 3 months we don't even need maintenance. So that type of prediction, okay, is very important. So that type of system conditioning monitoring have been done, in several of the appliances. Okay, it could be when motor, or it could be for generator, it could be for air conditioner, it could be for grid also. Okay, or it could be for in this case it could be for inverter. Okay, and not to do this system condition monitoring. Okay, you need to have a lot of data, number one. Okay, and number two, after getting the data, you need to have a set of systems or software, okay, which is going to analyze the data. Okay, so Internet of Things is going to help us collect the data in a remote fashion. Okay, and it's going to push the data to a centralized location where you have a system which is going to do this um, predictive maintenance estimation. And this data analytics is going to have a lot of data, so much data in fact. You cannot make this prediction in n node. N nodes computing capabilities will not be that much high. Okay, it's going to be embedded system, and embedded system may not have that much processing capabilities. So with the amount of data you have from a grid, okay, you may need to push this data to a remote location, and from there you should be able to observe the trend. So this device, okay, might possibly have a battery, and it will have a lot of sensors, okay, voltage sensors. If you have three-phase, grid, okay, so individual voltage sensors and individual current sensors. Three-phase means individually everything you have to measure. Okay, so current sensor could be a Hall effect sensor. It could be, or it could be a current transformer. Okay, it could be anything, right? So it's going to convert into something which your embedded system can read as voltage and send to somewhere for processing. Okay, and it should have a self-sustaining power supply. Okay, this embedded system. Okay, and it should be able to connect with internet. So basically, it should have a ability to sense, think, and act. Right. So it should also be capable of making some instant decisions. Okay, let's say some fault occurs, and due to the fault, okay, current level rises. Instead of sending this data to a remote cloud and that remote cloud to make decisions, okay, some decisions should be taken instantaneous, like operating a relay. Okay, in that case, the control unit should also be able to take some decisions, but not very critical. I mean, some critical decisions alone should be able to take. Okay, but it should not be like it cannot able to detect when the predictive maintenance should happen. Okay, so that requires a lot of data analysis. Okay, that will be very well taken care by the cloud provider. But in order to communicate to the cloud provider, your device should have a communication medium. Okay, so we have several types of communication medium required for grid. Okay, so you have something called power, data over power lines. Okay, so sometimes you'll have OPC cable, laser, not laser based, I mean optical fiber based data carried over to the along with the power line. So there are several communication medium available, which will be transmitting the data to a centralized location. Okay, so instead of this, getting the data by using a human being, noting it down for Excel sheet for further analysis, you will use possibly like yesterday what we spoke. Okay, we'll use for different types of parameters to be observing. We will use different types of sensors. Okay, and this sensor will be directly connected to the edge node. Okay, and we also spoke about yesterday one example of edge node that is called as compact trio hardware. Okay, which is capable of acquired data from the sensors and converting it into mission, computer processable data. Okay, it will be able to make measurements and this data, measurement data, could be either processed in the edge node itself for critical decision making or for data analytics to be done later. Okay, you can send this data to the cloud and make these measurements. Okay, to transfer data from your edge node to a cloud provider, you have several types of protocols available, IIoT protocols. Okay, so for service to service, we have AMQP, and for device to server, that is from your compact video to a cloud. Okay, you have MQTT, XMPP, and HTTP. Okay, several types are there. So we are going to see an appropriate protocol which is suitable for Google Firebase. Okay, so now for our purpose of learning, okay, we won't be using compact video. Okay, we have another hardware called as MyDeo. Yesterday we have already seen that MyDeo can be programmable using LabVIEW. Okay, so we have that connected already. Yesterday, sir, I explained to you about the capabilities of NRAO, and yes. And next is what after we connect this sensors to your Rio hardware. Okay, it could be compact Rio, or it could be MyDeo, anything. Okay, next is we need to know how it's going to be able to process the data and what type of data could it process. So if you take a typical electrical power system, it's going to be able to do power generation, or it's going to do power storage, power transmission, and power distribution. Okay, so all of these things are going to be combined together to form a grid. Okay, typically the main source of the grid is going to be power transmission line. Okay, after collecting the data from power generation, okay, you're going to go put the data to a centralized grid. Okay, where the different types of power generation units is going to be connected. Okay, everything is going to be synchronized. And power transmission is going to carry the data throughout the country and sometimes cross country. And then after that, you will distribute the power to different locations. Okay, for different types of consumers. It could be industrial consumer, it could be small industry, okay, or it could be residential functions. So in the power transmission and distribution, NI's role is going to be typically for power quality monitoring. Okay, we need to check whether the power waveform is properly transmitted from the transmission distribution, any distortion is there, okay, so on and so forth. And the transmitted power, whether it's equivalent to the received power, at least give or take the losses, okay, or we should be able to sense whether there is a very large gap between the transmission and reception. Okay, meaning that some sort of theft is happening somewhere. So you should be able to detect it. When you have a centralized system, you will be able to audit for the you will be able to do power auditing, right? So whether whatever they're generating, give or take the losses, whether the reception is happening properly or not. Okay, and smart distribution unit. These things, okay, let's say if you want to do the scheduling, okay, those kind of things, if you want to automate, if based on the demand required in an area, okay, you need to have a connected system which should be able to make this decision for us based on the trends, right? So where is NI tools is going to help for us? Okay, so it could be NI tools like compact video or these hardwares. Okay, it could be used in power generation. Okay, to automate the power generation systems, like let's say you want to implement a closed loop system of generator. Okay, turbine. So possibly some sort of NI tools could be used. It is being used. Okay, and during the transmission you have power quality monitoring. Okay, to implement the smart grid. Okay, to schedule the power transmission. So those kind of things you can potentially use NI tools, and to implement battery management system. Okay, so when you have a massive amount of battery, okay, not only for automotive, but for even batteries have been used in remote locations. Okay, so in that case of places, okay, so like in Australia currently, Tesla have implemented a battery based power supply unit. Okay, very large amount of batteries were used for the distribution. So in order to manage this system, so they need to have a battery management system in place. Okay, to do thermal management, to do some other types of information. And more importantly, when you have a several types of several places where you generate power, okay, and you need to synchronize these waveforms, the type of waveform you generate. Okay, synchronization is very important. And due to transmission, you have like inductance and capacitance effect during the transmission, and due to that, there will be a lot of phase difference. Okay, so in order to detect the phase difference and make a correction, okay, you need to have a phasor measurement units, okay, which will make this measurement of waveforms, and by making use of certain systems, it will check whether the whole total grid is in sync or not. Okay, to do that, each and every part of the grid, okay, within several locations, okay, with each and every predefined distance, okay, you need to have a measurement unit. Okay, it is going to measure this waveforms. It's going to be sent to some remote location along with timestamps. Okay, and check whether the waveforms everywhere is in phase or not. And let's say some sort of huge load, like inductive load or capacitive load, has been connected or disconnected. Again, we need to synchronize it, because due to that load, okay, we may have some sort of phase change, right? So these things should be considered. And not to make this, NI tools have been proven time to time to implement such sort of things. Okay, so if you take a power generation automation, okay, so you will have like power generator which converts one form of energy to another form of energy. Okay, so thermal power plant, nuclear power plant, or hydro power plant is going to convert this this is the potential energy to rotational energy. This is going to convert the thermal energy to potential energy. This is also going to convert the nuclear energy, which is going to be converted to thermal energy, which is going to drive the the turbine, right? So instead of just passing all the data, all the power to the turbine, okay, we may need to develop a control system, right? So depending on the load requirement, okay, we may need to allow the amount of water or burn the fuel required. Okay, instead of burning it all, we need to be able to make calculated requirements as to how much power is required at a given time. And based on that, you may allow more water to pass, or more fuel will be burned, etc., etc. So instead of doing this manually, okay, you might potentially use a controller. This is going to measure both inputs, outputs, and depending on the the closed loop system's requirement, you might control the flow of fuel, okay, so on and so forth. And similarly, for transmission as well, okay, so we may need to monitor each and every aspect. Like we are talking about this phasor measurement unit. You need to check what is the waveform phase here, and what is the phase here, what is the phase here. Okay, so each and every aspect, and the health of the grid also should be monitored. Okay, so is there any phase difference between the current and voltage, something like that. Okay, and here the health of the transformer, all these things should be monitored. So to do this, we may need to have an embedded system is capable of acquiring data from the given set of hardware, given set of asset. Okay, the asset is going to be the transformer. In this case, it's going to be the line itself. Okay, and here it's going to be again step-down transformers. And here also, we are going to monitor how much power is going to be consumed by the individual machines and stuff. And in order to monitor all these things from a remote location, okay, so everything should be continuously acquiring data, but having the data inside the hardware itself is not going to help. So in order to synchronize all these things, everything should be connected together. Okay, to make it possible, you might potentially use, LabVIEW. Okay, LabVIEW is going to be help to program these tools to the embedded system to acquire voltage, current data, etc. Okay, and from that location, you need to send it to a particular, centralized area where you might need to be able to calculate, let's say, losses or synchronization effect, etc., etc. Okay, so you'll be able to measure how much of phase difference occurs between the location 1, location 2, location 3, location 4, and not to get how much drift has happened. Okay, you will also take GPS timestamp as reference. Okay, with respect to GPS timestamp, you will potentially make use of the measurements. Okay, you will be able to compare whether there is a phase difference between the grids. So here if you see there is a we implement a PMU, phase measurement unit, using NI-RIO, okay, NI compact RIO. Okay, so where you'll have this measurement units inside the hardware. Okay, you'll make the connections from the voltage transformer, current transformer, okay, to this system, and this will be connected to your compact RIO platform, and internally it will have these algorithms, okay, which will calculate what calculate the voltage is required, and with that data it will be able to make some decisions, okay, maybe synchronization decisions, okay, and this data will be sent to some other centralized location which will make the ultimate decision. Okay, but how do we make this high voltage measurements now? Right, so every compact RIO will not directly have inputs and outputs. As we told, this is a modular instrument, meaning depending upon the requirement, you need to have an appropriate measurement device. Okay, so if you're going to make high voltage measurements, NI, this compact RIO card is going to come with, an appropriate measurement unit. So you have up to, depending upon the usage, you're going to have either a high voltage card or high current card. Okay, so since we are not going to make instantaneous voltage measurements, okay, sometimes we need to make some sort of, we need to apply some sort of algorithms, okay, which should be requiring not instantaneous values of voltage like 400 volt RMS, 300 volts RMS. It should not be able to do that. Okay, it should be able to get the waveform data. So when we have the waveform information, we could potentially make use of the waveform information to derive some sort of insights like whether something is going to fail, okay, or distortion is happening, okay, something like that. So we have NI cards up to 400 volts RMS line to neutral. Okay, so 800 volts RMS line to line. Okay, and up to this you can do. Okay, and since I'm making waveform measurements, okay, this can measure up to 50 kilo samples per second per channel. So you can get three-phase, the kind of oscilloscope type of measurements. Okay, so if you don't want that type of measurements, let's say you want like instantaneous measurements. Of course, NI also has a DMM cards available. Okay, where you can make instantaneous measurements up to 1500 volt RMS. Okay, so this is going to be very accurate, meaning any type of dynamic change, okay, occurs also. Since the waveform acquisition, any dynamically changing values also can be acquired. So yes. Okay, so it can go up to 400 volts RMS or 800 volts RMS line to line. Okay, if it goes above that, probably you may need to use a voltage transformer. Okay, so for instrumentation purpose. Okay, then convert it to something which comes at up until 400 volt RMS or 800 volt VRMS. Okay, or if it's a current measurement, we have cost up to 500 AR, ampere RMS. Okay, notice that it says RMS, which means it can measure up to 50 into 1.414 instantaneous values. Okay, so when you get the data, you just get the waveform data. If you apply some sort of logic there, you could you can convert the waveform information to an RMS value. Okay, it's basically root mean square application. And you have 3 channels, which means if you have 3-phase measurement, you can potentially make use of this. Okay, so you have a specific set of hardware which is going to help you get data, okay, from the grid. Right, so this type of cards can be used, and once you get the waveform, okay, you can make any type of measurements. Like if you want to get the RMS, of course you can do it. If you want to measure the frequency, once you get the waveform, it's pretty much very easy for it to measure the frequency as well. Okay, and plenty of things can be done, right? But typically this hardware will have raw data only. Now we need to think of an appropriate toolkit which is going to convert this raw data to something which can be subjected to some sort of analysis. Okay, so what type of toolkit we use? We have a toolkit called as electrical power toolkit, okay, which comes along with LabVIEW. Okay, correction is it will not come directly along with LabVIEW. A typical LabVIEW installation, a basic LabVIEW installation will have only 2 GB worth of files. Yes, ma'am.
No, sir. PPT is visible, sir. Someone is checking. Please stand.
No, everything is okay, ma'am.
Yes, sir. Everything is okay.
Okay, I thought you asked the question. Fine. Okay. So yes, so for doing this analysis, okay, after getting the data, we will be able to make use of something like electrical power toolkit, which comes as an add-on for LabVIEW. So typically, as we spoke, LabVIEW is it easily talks with several hardwares. Okay, if it is able to talk with several hardwares, okay, it will be able to get the data from external world inside your development environment. But after that, you need to make use of toolkits, okay, specifically used for different domains. Okay, so if it's a mission condition monitoring, you might need to use a vibration toolkit. Okay, for grid monitoring, okay, we may need to use an electrical power toolkit. Okay, it is going to get grid related data for us to analyze. Okay, so where you see it? So you can see that in LabVIEW. Okay, let me close this and open LabVIEW. As we spoke yesterday, this LabVIEW. Okay, so you already seen what LabVIEW is yesterday. Okay, and yesterday we started working with the hardware as well. Okay, so the programming of this toolkit is not only specific to the LabVIEW in your computer. Okay, it is also very specific to your hardware as well. What I mean to say is, since your Rio platform is going to acquire data of voltage and current, okay, it should also be able to process this data. So we have this LabVIEW opening up. Right now we will be having a MyRio hardware, okay, using which we'll try to process some sort of data using electrical power toolkit. So it takes some time to open. Yeah. So let me say that this is going to be power monitoring. Okay, power monitor. Okay, my desktop. I have my Rio already connected to my Rio computer. So I'll just click finish. And it will generate a development environment where I can start writing the code automatically. So even though we have specific hardware related for acquiring the data, you could see that your Rio also has like 12 analog inputs. Okay, but this analog inputs, the specifications are very clearly that if you look at the specifications, it could read only up to plus or minus 10 volts. But realistically speaking, our voltage will be, in terms of 400 volt RMS or in kilovolt range, right? So that's why NI say that providing you the option of the external part. Okay, but if you are familiar with signal conditioning, okay, you could potentially design an external circuit. This is going to convert this 300 volt RMS or kilovolt range of RMS. Okay, it's going to attenuate to something like plus or minus 10 volt range. Okay, so you could use several types of circuits. Okay, there are several types of circuits which can be designed. Okay, with isolation. Okay, to convert that level of high voltage to a low voltage stuff, and that can be subjected to unlocked execute condition. But instead of doing that, you have a separate card which is already developed and already tested and already certified by a third party company that this is working fine. And several companies also use it. Okay, now I just have to program under my view. So I'll edit this. And let's say I'm going to process three-phase power. Okay, when I want to process three-phase power, I need to be able to acquire three-phase power. But unfortunately, my hardware of video cannot be able to acquire that much level of voltage for now. Okay, because they don't have signal conditioning. But still, this hardware is capable of processing three-phase based, information if it is able to acquire it. Okay, so in our tested algorithm at least, okay, we should be at least able to generate certain type of data in your lab environment. Okay, and not do that. You have certain set of functions called as signal processing functions available in LabVIEW, which can be used to generate waveforms. Okay, so yeah, so you have signal processing toolkits, okay, which can be able to generate certain type of waveforms. So these functions can be used to generate waveforms. Now I need to generate a three-phase sine wave. There is no such thing as separately a three-phase sine wave, but what I have is a sine wave function which can be used to generate waveforms. I just need to drag and drop it, and since this three-phase, okay, I need to have two more copies of it. And here you can see that this program has inputs. Okay, since LabVIEW will be based on input and output, you need to give some inputs to it. is this frequency, and for in the 3-phase, okay, so we will assume that everything is going to have same frequency of either 50 hertz or 60 hertz, whatever is better for it. If we're just simulating it, we're not acquiring data. Okay, if you want to acquire data, of course, you have certain function called as RIO functions. You can acquire analog input, but you have to know that this will not be power levels. Okay, so this particular hardware can only be connected plus or minus 10 volts. Right now, we are just not going to connect it to absolute power. So right now, in order to test the capability of the hardware, we just simulate it. Okay, so we have generated this waveform and amplitude. I wish I can give 230, but 230 volts does not equal 230 volts RMS. Okay, in order to measure, if I measure, it should come as 230 volts RMS. So if I give 230 here, it states that its maximum value and minimum value is just 230. Okay, and if you measure the RMS value there, it will not be 230. Okay, if you want to get 230 volts RMS, potentially you need to give like 230 into 1.414 voltage. Okay, in order for it to be 230 volts RMS. So basically, you have to give here 325 volts. Like this. And finally, we have phase. Okay, phase is going to be different for all three. Okay, this is 0 phase. Okay, here you can give one input like 120-degree phase. And here you'll have 240 phase. Okay. So we have individually each phases. Okay, but this is since this is 3 phase, I will have to combine it into array to process it efficiently. So individually we have waveforms like R, Y, B. Okay, in order to process them at a time, I use an array function. Okay, in our LabVIEW also we have arrays. Okay, just like any other programming language. Okay, but every programming step what we do here is graphical. So I just need to combine all these things together. And right now we're just visualizing it. Okay, in order to visualize, we have certain tools available in LabVIEW called as waveform graph. To visualize it. So I run this program, it's going to ask me whether I want to save it. It's going to, and moreover, this particular simulation is taking place inside the hardware. This generation. What will happen is your LabVIEW program you're writing in computer, when you click the run button, the program will get uploaded inside your hardware, and in your hardware also you have LabVIEW. Okay, so that data, the program will go inside the hardware, it will get executed, and data will come back to your computer again. And later point in future, let's say you don't want to simulate it, you can remove the simulation waveform and feed the data of the actual IO data. So right now it's getting deployed. I'll save it, close it, and here you can see this sine wave data. Okay, here you'll be able to see full 1 second period. You can reduce it by editing the last value alone. Okay, and moreover, you can also change the customization of appearance. Okay, so first plot is going to be red. Okay, this is going to be R plane. Okay, it's going to be Y plane. And this is going to be B plane. So you can also increase the thickness. So you can visualize it like this. Right. So the idea is one should be able to process the data, but also another important thing is visualization. Okay, so other tools I'm not sure when it comes to visualization, we may need to tinker around with several external libraries. Okay, but for LabVIEW, the visualization is so very important that it's actually a part of the program. Okay, because everything is visualizable in LabVIEW, so you have the inbuilt graph function available. So this is just a test waveform which is generated. And I have to process it. Okay, since this is with respect to grid-based data, okay, you have a separate toolkit called as electrical power toolkit, which is basically a toolkit specifically used for electrical power measurements. Okay, so it could be used to do power measurements. It could, if you're going to work with motor, okay, motor-based data will be measured. Okay, or with respect to power quality, you have several functional programs available. Okay, for implementing a synchro phaser, okay, also you have a separate toolkit available. If you want to implement a cost production functions, okay, you have functions available. Or let's say if you're going to work with electrical vehicles, okay, you have electrical vehicle specific tools available. So these are things which are available inside electrical power tools. But right now we're just going to make measurements with respect to electrical power. Okay, so there are specific functions specifically used for that alone. Okay, so you already got the measurement from your hardware. So it will be coming like this. Okay, so let's say you want to make some analysis. Okay, you want to make some measurements. Okay, so raw measurements are here. You need to convert to something like engineering units. So you have a function called RMS function. So ideally, this when you place this should come immediately. But computer is a little bit slow, so you can see that it's very low a little bit. So ideally, it's not just to take this much time, but basically what happened right now is when I try to click and place it, this is going to go inside the hardware. All right. So Let me check. If it's taking too much time, okay, potentially what you can do is, for development alone, you don't need to do it in the hardware. Okay, you can do it in your computer. Okay, you can just right click on below, just change it to computer. So that development you can do it in here because just where it's working, then you can deploy it in the hardware. Okay, so we collected a three-phase waveform, and now to make analysis with respect to three-phase waveform, we just need to make the connection here. Okay, so we got the waveform here, for which we need to find the RMS. So what you'll get here is the RMS values. So if you create indicator, I'm going to get RMS value as a array meaning for each and every phase. So in this program, you can see that for each and individual phase, it's going to measure the RMS. Okay, so this data right now is just similar data, but in future you can replace it with the hardware measurement. Okay, if you want to find the frequency, you can just place the frequency block and connect the waveform to it. Okay, which is going to in turn give you the actual measurement. Right? Then let's say if you want a fundamental vector, okay, for which you need both voltage waveform and current waveform. So voltage waveform we have it here. Okay, but for current waveform, I'm just going to have copy paste of this waveform. Okay, and instead of 325 voltage, I'm just going to give 14.14. Okay, similar to 10 ampere current, RMS current. This is for voltage, three-phase voltage is three-phase current. And the phase difference, if you see, all of them are same, so which means we can assume that it's an R load or so, something like that. So you'll get the voltage fundamental vector and the current fundamental vector. Okay. So my right click can create an indicator. It's going to give you the fundamental vector values. Okay, in terms of complex numbers. Now we are not very good at complex numbers. I mean, in terms of numbers, if you see the vectors, it's not very, very interesting. So what you can basically do is, typically if you right click on your front panel, for every 12 bit, there is a separate control indicator available. Okay, in this case, we have this vector diagram based indicator available, which will help you to visualize this, stuff. So we can basically connect this to both voltage and current vector diagram. Okay, and connect it to your hardware. So you can get it here. Okay, since it's having both same faces, you can see something like this. Okay, but if you adjust the phase, you can see the difference in diagram. So since humans are visual beings, it's better if you use a visual indication. So we have vector diagram like this. And not only will you be able to measure the fundamental vector and stuff, okay, you can also make measurements of power and energy. Okay, meaning you can make this Rio hardware as a power monitoring tool. Okay, the complete power monitoring tool can be done. Okay, so for power, you just need to feed the voltage waveform and current waveform. Typically for AC, people will say, okay, V, I, and you need to give the theta value as well. I mean, power factor also. But in this case, since you're feeding the waveform, you are using the waveform itself, which will be able to calculate the power. Okay, you don't need to give the power factor. Okay, it's going to find the power factor for you, to be honest. Okay, to this, we just need to fill the waveform, voltage waveform, current waveform, and what you'll get is the power values. So you'll get power values for each and every phase. Okay, for each and per phase values you'll get. Okay, so if you want to convert this individual power phase value to an three-phase power, you need to make calculations. So that if you are I'm sure everyone can do that, right? So once you have power, okay, you can also measure the energy as well. So power is going to be energy, energy is going to power into time, right? So if you have the power, so by giving the amount of time at which this power has occurred, you will be able to get the energy as well. Okay, that might sound easy, but you need to calculate the interval, the waveform's time period. Okay, so to calculate the time period, you need to extract certain information from your waveform. So to extract information from waveform, we'll go to waveform functions available in LabVIEW. I'll get data like the time period of your waveform. Time period of waveform and the total stuff available. Right? So this is for each and every sample time period. Okay, this is total number of samples available. So if you want to know the total time period, you will basically multiply these two together. Okay, we're not directly multiplied, of course. This has all the information. I just need to find out what is the size of it and multiply it. So that's going to give me the interval. So it's loading again. So basically, if you observe, the total time period here is 0 to 1 second, and that's what we found by finding out the length of the waveform and the sampling time of the waveform. So when you multiply both of them, you're going to get a total duration. Okay, so if you give that to this function, that is going to be power into, it's going to integrate the power to energy. So internally there will be functions available. Okay, it's going to return you the energy values. And energy value right now is just giving for the 1 second. Okay, but if you are able to run this inside a loop continuously, okay, so every 1 second, let's say you're trying to get the data, you can see that this will act like an energy meter. Every 1 second you'll acquire data, 1 second data, you'll acquire it, then internally you'll process the data and you'll present the energy values. This is the power, this is the energy. So this could act like an energy meter. So this is to say that your hardware not only is capable of acquiring the data, but also is able to process it in the node itself, edge node itself. And after processing the data, potentially you can transfer it to cloud. So now one might wonder how that is going to be possible. Yes, we're going to see that. Okay, let's say this hardware is going to collect the data and processing it here by using this electrical power toolkit. Grid-based data is there. Okay, this is just a you can say a non-exhaustive list of functions which could be executed. Okay, immediately after cutting the data. But if you see, there are several other more functions available. If you go to electrical power, okay, you can see that specific to power quality also we have events like if you want to check whether this swell has occurred, a dip has occurred, okay, harmonic information. So all this information, okay, balance, not to check whether this unbalancing is there. Okay, so there are specific functions used for specific purposes. Okay, so those things are going to be available here, right? And with respect to protection also, we have certain functions available. And if you're going to work with the electrical vehicle, you have like the efficiency, not to calculate the efficiency of motor after measuring. Okay, you have certain functions which is going to be useful only for calculating that. Okay, so now let's say this Rio hardware is connected somewhere in your the grid, somewhere in desert or somewhere along the grid lines. It's acquiring this voltage and current waveform. Okay, and it is also processing this data also. Okay, so this is happening somewhere remotely where internet is available, either through GSM or either through the power over data over line connection, right? So along with the power lines, possibly a OPC based connection also will be sent. So if you through that also maybe you have the interconnection. Okay, potentially. So these data should be connected somewhere. Am I right? So how do we achieve that? Well, in order to achieve that, okay, so right now we have the data which needs to be pushed into, let's say right now for a remote connection, we might make use of some sort of cloud based connection. Okay, and using the cloud connection, we can make this connection, make this observation worldwide. okay, by just tweaking some sort of rules. So how do we do that? So we make use of Google's Firebase. Okay, so Firebase is typically which was used by app developers, computer cell phone app developers to get their data, client-based data to there and just process it. But measurement-based engineers, okay, you realize the potential of putting the data into the cloud, not only the data of the cell phone users, but also data with respect to voltage, current, power, those things. Okay, or embedded related data can also be put and fetched back, and the data could be put inside remote location, and it could be fetched. This hardware should be connected to internet, and it will continuously keep on putting the data. Okay, and fetching can also be done, and we need to make use of some protocols for that, right? Yes. So how do we potentially work around that? So right now I just need to transfer it back to I've created this function, the program, and this was running perfectly fine in my computer. Okay, now I just check it with my hardware. So whatever program I written is getting converted to something which my hardware can understand. It's going to get compiled, and after compilation it will execute. Okay, it takes some time because a lot of process is happening at the back end. So let's see what we have to do until that. Okay, so basically we are going to push this data from to Firebase to a hardware connected to internet. So now we have to think about how we have to connect the internet, connect the hardware to the internet. Number one. Number two, how do we transfer data from a computer to the cloud? That is number two. Then how to view the data in the cloud. So there are several places here play. Okay, first we need to configure the cloud to accept this data. So now if you see the same program, if you see it's running under my view. Okay, if I stop it, stop. So in order to push this data from my hardware to a cloud, there are several protocols we discussed last time. Okay, but since Firebase is not really a sophisticated cloud, okay, it supports HTTP protocol to be used. So using HTTP protocol, we can push data from your hardware to your cloud. To do to okay, to configure your cloud. So I'm just going to configure the Firebase cloud to accept data from your hardware. So I'm just going to open the Firebase. Okay, so if you see this is the Firebase cloud, I can just get started. And here I have used several projects. Out of which I'm going to create new project. Okay, something like IIoT, Rio. Okay, it's going to ask me for certain questions. I'm just not going to answer everything. I'm just going to click continue. And I'm just going to use the default account for Firebase. Okay, anyone can create Firebase. It's going to be free. And once you create it, this project is going to be created. And as far as Rio is concerned, your Rio should be connected to internet. So to configure a Rio to connect to internet, if you see, this is the Rio hardware available. Okay, yesterday we already seen it. So along with several other options available. Okay, for in order to configure a Rio to connect to internet, we have something called network settings available. I just need to configure my Rio to connect to internet. So let it load. Meanwhile, I'll configure my Firebase. So this is the Firebase store. Okay, so out of this, a lot of databases things will be available. Out of it, I'm going to use real-time database. So it says stores and sync data in time. So I'm going to do create. It's going to ask from which location. I'm going to go for nearest one. I'll give next. Okay, I'll copy this. Okay, I'll copy this. And I'll give, because basically, sometimes you should be able to access the data. Okay, and this is Google Firebase also requires security. Okay, IoT also requires security. We may be able to configure who can access data or not. Okay, so security rules are written here. By default, you can give lock mode or test mode. Okay, right now I'll just give for lock mode and I'll just give enabled. Meaning no one can access your data. So if you see, this is the HTTP link, which will help me access this hardware. Okay, so if I use this link, HTTP link, okay, I can push the data from any app application. But before that, I need to edit the rules. Okay, it says no one can access the data. For now, I'll just give true. So everyone can access my data. Okay. Now to the different adapters. So let us search for adapters. Okay, before that, we will configure your program. Okay, basically we told that we are going to use HTTP to push data to your cloud. Okay, and LabVIEW, yesterday itself we have seen that there are several data communication functions, okay, which can help us transfer data from one platform to another platform. In this case, from my Rio hardware directly to cloud. Okay, in that case, my Rio should be connected to internet. So I have functions of HTTP available to make it possible. So in LabVIEW, there are sequence in order to access data. So first I have to open the request, then I have to use put. Okay, so I can use either put or post. Okay, then I have to close it. So this is a sequence for any LabVIEW program. Okay, then I close it off. Okay, apart from programming, since LabVIEW is very specifically used in several industries, hardware-based industries, we also pass some wires for error wires. So basically, exception handling. Okay, now do exception handling very simply. Okay, so there are inbuilt stuff which is available inside LabVIEW. And now to stop this program, you can either use the stop button available, or when error occurs due to network connectivity or something, your program should stop. Okay, now I need to post the data of these values. Okay, at least one value I'll put it, if not all. But if you see, this is where we give the error, URL, create a constant. This is basically string data. Okay, I need to give this URL. And potentially I also need to give the variable name as well. Okay, like energy. The energy is the parameter which I'm going to pass from there to here. And there's a specific format which you need to pass called JSON. JSON stands for JavaScript Object Notation, which I will pass data from. Okay, next I need to pass is buffer. The problem here is, if you see LabVIEW data types, LabVIEW inputs and outputs are colorful. Okay, it might look colorful, but the color is actually called as data types. Okay, in other programming languages, we specify the data types like variable, or we specify the names of the data types. Like, for example, integer means we specify int, string means we specify str. Okay, like that we'll specify. But in LabVIEW, everything will be color-edged. Okay, so if you see, this input is actually pink in color, and energy values are basically like orange color. So if you want to connect it from here to here, the connection is not possible. Okay, it will produce a broken. So in that case, how do I pass the data then? Then basically, we need to extract these values and pass it, and convert into something your HTTP can understand. Okay, basically this data type is string data type, so I need to convert the data type, whatever I pass here, to string and pass it. And it's not any string. Okay, we converted something called as JSON string. That is .json. So all three pairs data will come. I will just extract only the one page information alone, because if you want to pass, I need to again work a lot. And from that one, I will extract only, things which are required for me. Okay, active energy, apparent energy, reactive energy. And I cannot directly pass it. Okay, I need to build a reference which is acceptable. So I'll build this reference. So active energy, apparent energy, then reactive energy. Like this, I build some reference. Then I'll combine it again. Then I send it inside. And this is going to produce me the JSON string, which can be acceptable by my HTTP function. So we'll just test out. I'll run this program. And if you see here, you should be able to see the data ideally. But the data will not come here because number one, I'm running this program under my Rio. Okay, number two, my Rio is still not connected to internet. Okay, it's still loading for network adapters. Okay, basically it's very busy. Okay, I'm not sure what's the problem. Yeah, it came. Okay, so now I just need to, right now the wireless adapter is disabled. I'll just give it connect to wireless network. And I'll try to search for network is available. Okay, maybe my cell phone, hotspot. Okay, and I have to give the password, username and password of my hotspot. So which I have to enter here. Then I just give save. And I'm not able to show anything here, but right now it says that my Wi-Fi is connected. LED of my Wi-Fi button is blinking continuously. Okay, but now if I run this program, the data should be available over here. Okay, some sort of error is there. So let's check it out. Okay, I'll try explain running this under my computer. Okay, now if you see under my computer, if I execute it under my computer, the data from my hardware directly comes to my uh, real-time database, which is Firebase. Okay, it is not coming from my hardware. I'm not sure, some problem is there inside the hardware, but right now instead of my hardware, I'm using the same program under my computer. So whatever is getting generated here, okay, it's getting pushed by using HTTP. Okay, and to my they're putting the data inside my cloud. by using this HTTP protocol, and that data is real-time data which is getting updated in my cloud dashboard. Okay, you can see the data here. Like that, you can keep on putting as much data as you want. Okay, and it need not be only number, number. Okay, it will be true or false value as well. Okay, and not only is it bidirectional, I mean not only is it unidirectional, you can send data from some other place to this cloud as well. Okay, so that level of flexibility will be available. So ideally, this should also run inside your hardware. Okay, but probably something has gone wrong in installation. Okay, so it's not executing inside my Rio. Okay, but if you reinstall it, it should come properly. So this is about along with instrumentations, and you'll be able to make these measurements, and this data will be transferred to a cloud. Okay, after cloud, depending on the cloud which you use. Okay, this cloud, you can just acquire data and just display it in real time. Okay, but potentially you can make use of some other type of cloud which can use this data for some data analytics. Potentially you can do condition monitoring and stuff. Okay, you can deploy some algorithms, like if you take Amazon, okay, it could do a lot of stuff. Okay, so that you can potentially explore. Once you get the data inside the cloud, then after that it's going to be up to you to do what you want to do. Okay, but acquiring data is the first step. If you're familiar with that, then it's going to be others is going to be going, in the flow. So that's about it, I guess. If you have any questions, please let me know. So let me know if you have any questions. Okay, you can unmute and ask the question if you have. Okay, so no questions in that case.
Excuse me, Mr. Raj, this is Prasad. I have one question.
Yes, sure.
How we can store the data in the database? Can you explain on that? Means if we want to store the data for a couple of time period, let us say for 1 day, how we can able to store that in this particular platform from the LabVIEW data?
Okay. Right now it's just going to do a real-time database. It's just going to show instantaneous data, but you have to make some configurations. Okay, where you can initiate the storage, like each and every data, whatever was acquired. Okay, so in here, whatever data was displayed. Okay, you have to configure it to store the data. Whatever data has been coming, okay, it will be stored line by line. Okay, but for that you have to make some configuration. Okay, by doing the configuration, okay, it will store every instantaneous data whatever was received, okay, into the storage. So like you can also make a custom arrangement, like every 1 minute you can store data or something like that. Okay, but of course it requires some sort of configuration to be done. Okay, and that configuration will, store the data.
Okay, so the configuration has to be done on the LabVIEW environment or in the
No, not LabVIEW environment. It will be done on the Firebase environment.
Okay. Okay.
But if you want to store inside the hardware, okay, in that case, you can store by using file functions in LabVIEW itself. We have the file functions.
Yes.
Okay, where you can data log it. Okay, so once you data log it, you can send it inside the cloud as a file and you can store it. Okay, you can even access Google Drive also. Okay, once you have the required toolkit, you can put that file functions. Okay, so like you can store data in a CSV or Excel sheet. Okay, and you can send it to Google Drive for login. So that type of stuff also can be done.
So can we extract the stored data, which is from the LabVIEW information, can be extracted through cloud? Is it possible through Firebase? Means already the raw data which is collected already.
Okay, yes, sure. Once we get the CSV data inside the cloud, potentially we can make use of the internally available functions to read the CSV data and possibly to process it. Okay, such type of process can also be done.
Okay, thank you very much.
Yeah, sure, thanks. So if no more questions, I guess that's it. Okay, thank you very much for providing this opportunity to give my insights on how LabVIEW can be used to implement these solutions. Okay, not only is it going to provide you with software solution. Okay, you also have the plenty of hardware-based ecosystem also. Only by combining both hardware and software, okay, we'll be able to derive the IoT. Okay, so from edge node to the cloud-based solution is available in NI itself. Okay, apart from Firebase is actually third party, of course. Okay, but of course we have something called NI System Link, which is NI provided cloud. Okay, so all these things can be potentially done by using everything can be done in NI ecosystem itself. But System Link is not free. Okay, so that's why this total demo was done on Google Firebase.
Yeah, Mr. Raj, this is Prasad again. Actually, the content you have presented is extremely well, and I request if you can suggest any kind of reference to follow, the kind of data logging in Firebase. You did that JSON unlinking and all those process. If you could suggest any kind of reference to the participants so that they can explore in near future. Because, this one day would not be able to do all the things, but if you can able to provide any reference to explore, so that it can be helpful.
Some sort of file, because mostly we'll send reference materials. No, so with that reference material, I will give the steps which is required to configure to store the data. Surely.
Yeah, that is good. Thank you so much.
Yeah. So I'll stop right.
Pooja ma'am, over to you. I think the session has been concluded. Hello. Just a moment, please. We'll supposed to conclude the session.
Okay, some people have requested me attendance link. Attendance link will be, please ask ma'am, Pooja ma'am or someone else. Yeah, so thank you everyone for giving this opportunity. I will just once again I will drop my contact information. If anyone has any questions regarding the implementation of IoT stack using total NI technology, you can if you have doubts you can just contact me, or else that's about it from my side. I'll just hand it over to ma'am.
Yeah, thank you very much, Mr. Rajkumar, for your intuitive and detailed presentation and explanation of the LabVIEW interfacing, especially for smart grid architecture is concerned for various applications. So, on behalf of EEE Department of Gayatri Vidyabhushan College of Engineering, I would like to thank you for your time and explanation of the hardware interfacing for all the participants of particular workshop. So I would like to thank you very much for your intuitive presentation, and thank you for sharing your details also for the participants, and it will be available for all of you. If you have any queries, you can have a contact him. So thank you for your valuable time, and with this I would like to conclude this particular session, and we will meet on the next session. Thank you so much.